Hello, and welcome to an introduction to digital electronics. So, this will be the first part in the series, which will deal with digital circuits and logic gates. Have you ever wondered how computers work? For the most part, you know that it uses electricity because you have to plug in a computer, otherwise, it won't work, or you'd have to charge your phone or your laptop. But how does electricity, which is the flow of electrons in a conductor, enable such amazing things as video games, artificial intelligence, and even you watching this video right now? But how does it really work under the hood? So for one, you might know that computers use binary, which are zeros and ones. Computers use the binary to store, manipulate, and process data. This is why they're called digital devices. But how does it all tie in with electricity? It's actually simple. So the zeros could be represented as a low state, which you can show with a bulb that's off. And the high state, 1, could be represented with a bulb that's on. But in a computer, they're not bulbs. They are represented as different voltages. And the magic of operating in these states, these zeros and ones, is performed by special circuits called digital circuits. And this leads us to the field of digital electronics, which is a field of electronics involving the study and development of such devices. These digital circuits are the fundamental parts of a computer, and the smallest building blocks of these digital circuits are called logic gates. They are special circuits that perform logic functions on these binary states, the zeros and ones, that eventually lead to the execution of commands on the computer and other processing that the computer does. So, processing this video, for example, playing a game, editing a document, and anything that your computer does, it all boils down to binary. And the processing of this binary to now these actions that your computer does is done by these logic gates. There are many types of these logic gates, and each perform different operations. And we can combine them to perform various operations and even use them to create circuits that can store data, as we'll see later. So I plan to make these videos a series. So we learn about these logic gates and how they operate in simple terms. And we'll also do some experiments of our own and design some of our own custom circuits. Later in the series, we'll also go through Boolean algebra, which will help you understand how to design these digital circuits. Boolean algebra is a branch of mathematics that deals with variables that have two distinct values, true or false. In our case, that's a 1 and a 0. And it's very important to the design and operation of digital circuits and computer systems. So we'll go through that in upcoming videos so that you can design circuits that can do some cool stuff. Let's get started with logic gates. We've seen that there are various types of logic gates, and we'll look through each and every one of them, looking at how they operate and generating truth tables for each one of them. Plus, we'll only represent the low and high states as 0 and 1 throughout the series for the sake of simplicity. We'll also use symbols to represent the various logic gates, both in the diagrams and the schematics. The first type of gate we look at is the AND gate. So this performs the AND logical function. So it's a type of gate whose output is 1 when both or all of its inputs are 1. So this is the symbol for the AND gate. So to simplify things, we'll put A and B as the input and Y as the output. So for example, if both A and B are 1, then the output is 1. So we'll look at a few more examples like this as we continue learning about how the gate works. Another example is when A is 1 and B is 0, then the output is 0 because not all of them are 1. So we can continue trying different combinations and recording the outputs. And this we can store in a table, and this is known as a truth table. For example, here our first entry, when A and B are 0, then the output is also 0. When A is 0 and B is 1, the output is 0. When A is 1 and B is 0, the output is 0. When both A and B are 1, then the output is also 1. And that's the only time when the output is 1. So this table that shows all of the different combinations of the inputs and the output is called a truth table, and we'll look at many of them throughout the series. Also note that such gates as the AND gate can have more than 2 inputs. It can have 3, 4, 5, and as many as required by your design. But the working principle is the same. Its output is only 1 when all of the inputs are 1. To help us understand how these gates work even better, we can use online simulation tools to help us practically see how they work. So for this, I'll be using circuitverse.org. I'll put the link in the description of this video, and you can log in and try it yourself. But there are many other simulators out there that are even better and offer more components. But since this is a simple logic gate, there's no need to use a complex one. So for the input, I'll just be using some binary input, which can have both the states either 0 or 1. Then I'll choose the AND gate. From the shape, you can tell that this is the AND gate. But this one has 2 inputs, 1 output. Then for the outputs, I'll be using an LED. Then I'll try out some different combinations of the inputs, and we'll see whether the LED lights. It will only light when both of my inputs are 1. And that's true according to our truth table. The OR gate. It is a logic gate that performs the OR logical function. And this is the symbol for the OR gates. Just like in the AND gates and any other subsequent gates, we use A and B as the inputs and Y as the output. The OR gate is a logic gate whose output is 1 when at least one of its inputs is 1. That means that A can be 1 and B can be 0, and the output will be 1. Or B can be 1 and A can be 0, and the output will be 1. So this is an example. So A is 0 and B is 1, the output is 1. We can now look at its truth table. When A is 0 and B is 0, then the output is 0. When A is 0 and B is 1, the output is 1, because at least one of the inputs is 1. When A is 1 and B is 0, then the output is 1. When both A and B are 1, then the output is still 1. So the output is only 0 when both or all of its inputs are 0. Just like the AND gates, the OR gates can have multiple inputs. It can have 2, 3, or as many as you need, but it works just the same. So here we have 3 inputs, and one of them is 0, but the output is still 1 because at least one of the inputs is 1. So even if we had just one of them being 1 and both being 0, then the output will still be 1. We can also try this in the online simulator, and we can try some few combinations, and we'll see that the LED only goes off when both of the inputs are 0. Otherwise, it stays on. The inverter, also called the NOT gate. So it produces the inverse or the complement of its input. So for example, if it's given a 1, it produces a 0. If the input is 0, it produces a 1. This gate only has one input, so we'll call it A, and we'll call the output Y. When A is 1, the output is 0. When A is 0, the output is 1. This one has a simple truth table. It's just the inverse of the input. Also note that the inverter has a small sort of circle or bubble at the end. It's usually used in digital circuits to show that there is an inversion. We'll see more of that as we continue along in the series. We can also try this in the online simulator, and we see the same effect. When the input is 0, the output is 1, so the LED lights. When the input is 0, it still remains 1. When the input is 1, then the output is 0. The LED goes off. So far, we've looked at some basic gates, the AND, OR, and the inverter. We can also get some more gates by combining some of them. So the next one we're looking at is the NAND gate. You might have guessed from the name that it's a combination of the NOT gate or the inverter and the AND gate. Essentially, it produces the inverse of the output of the AND gates. So as you can see, the symbol looks like the AND gate, but with that small circle or bubble at the output. Just like the other gates, the inputs will be A and B, and the output will be Y. If we were to split the NAND gate, it will look something like this. Basically, a NAND gate with an inverter at the output. For example, if A was 0 and B was 1, the output of the AND gate will be 0. This 0 is fed into the input of the inverter, and the final output becomes 1. So essentially, the output of the NAND gate is the inverse of the AND gate. And the same is true for the truth tables. Where the output was 0 in one, the output is 1 in the other. And where the output is 1 in the AND gate, the output is 0 in the NAND gate. There are some useful properties of such gates we'll get to look at later. We can also check out the simulation. Notice the LED only goes off when both inputs are 1. We've looked at the NAND gate. The next gate we look at is the NOR gate. You could have guessed it already. Yes, it is a combination of the NOT gate for the inverter and the OR gate. So this is the symbol, and it looks like the OR gate, but with that circle or bubble at the outputs. If we were to split apart the NOR gate, we'd get an OR gate with an inverter at the output. So the NOR gate inverts the output of the OR gate. For example, if A was 1 and B was 0, the output of the OR gate would be 1. That 1 is fed to the inverter, and the final output becomes 0. So the output of the NOR gate is the inverse of the output of an OR gate with the same inputs. The same can be seen in the truth table, where the output was 0 in the OR gate, the output is 1 in the NOR gate, and vice versa. We can also check out its simulation. Now that we've looked at the NOR gate and the NAND gate, I had mentioned that such gates have some useful properties. And these two gates, the NOR and the NAND gate, are known as universal gates. And this is for a reason. It's because they can be used to implement any other type of logic gate. Essentially, if you had a circuit that used a combination of the AND or an inverter, you can use either of these two gates to make the same circuit without using any of the other gates. For example, let's say our circuit had an inverter. We can make it using a NAND gate alone without any other gate. So here in our example, we've connected both inputs of the NAND gate, and as you can see, when the input is 0, the output is 1, and when the input is 1, the output is 0. essentially our NAND gate has now become an inverter, and we can make other gates like the AND or also using the NAND gate or the NOR gate. We'll see more of this once we go through Boolean algebra, once we know how to simplify and design some of these logic expressions. It would make much more sense. Now that we've seen the universal gates, we'll also talk about some special gates, and one of them is the XOR gate or the exclusive OR gate. Now, this one is similar to the OR gate, but it has a special property. Unlike the OR gate, where the output is 1, if either of its input is 1, for this one, only one of the inputs should be 1 for the output to be 1. Meaning that if more than one of the inputs is 1, the output will be 0. That's why it's called exclusive OR. Only one input should be 1 exclusively. Now, this is the symbol of the exclusive OR. It looks like the OR gate, but it has some sort of arc at the back. For example, here our inputs A and B are both 1. If this was an OR gate, then the output would have been 1. But since it's an XOR gate, the output is 0 because more than one of the inputs is 1. We can also check out its truth table. When both A and B are 0, then the output is 0 because none of them are 1. When A is 0 and B is 1, then the output is 1 because only one of the inputs is 1. When A is 1 and B is 0, the output is 1. However, when both A and B are 1, then the output is 0 because more than one of the inputs is 1. This gate is very useful in some circuits that we'll see in the future. If you might have noticed, the output is 1 when A and B are different, and when they're the same, the output is 0. This is one of those interesting properties of such gates, and it will become really useful in some circuits we'll design in upcoming videos. We can also check out its simulation on Circuitverse. It works just the same as we've seen in the truth table. In addition to the XOR gate, there's the XNOR gate, which essentially does the inverse of what the XOR does. We can see that little circle or bubble at the output. Essentially, the output of the XNOR gate is the inverse of the output of the XOR gate given the same inputs. We can also check out their truth tables. And we see that where the XOR produced a 0, the XNOR produces a 1. Where the XOR produced a 1, the XNOR produces a 0. You can also notice the same property, but now inverse in the XNOR gate. It produces a 1 when both of the inputs are the same, but it produces a 0 when both inputs are different. Now we can see a pattern happening here, and we'll explore more in the future about it. So those are the gates that we'll cover in this video: the AND gate, the OR gate, the inverter, the XOR gate, the XNOR gate, the NAND gate, and the NOR gate. From now on, let's look at the physical aspects of these gates. We've looked at how they work on paper, but how are they actualized using electricity and different components? We have seen some logic gates and what they do. We still don't know how that applies in a real circuit. How does it look like physically? All we've done so far is just talk about them. There are many ways to make a logic gate. They can be made from transistors or CMOS, which stands for complementary metal oxide semiconductor. One of the most common ways to make it is using transistors. For example, in a modern CPU, there are billions of transistors. Each have been arranged and connected in such a way that your computer can utilize these circuits to perform its operations. The design of a CPU And subsequently, its architecture using these transistors and other components is an entire subfield of electronics itself. For the sake of this video, we'll stick to the basics. You won't need to remember how each of these components work individually. However, for the sake of our own interest, we'll go through the transistor. It's a small device, but it has had an enormous impact in the subsequent development and evolution of our computers. It may not be necessary to remember how it works for the sake of this series. However, I feel it's important that you have a rough idea of how it operates so that you understand some of the examples that will be in the video. For a more complete or wholesome understanding of how the transistor works, I'll link some videos in the description. Some electronics knowledge will go a long way. However, it won't be necessary for you to understand the examples. I'm not an expert myself, but I'll try to explain where I can. So let's get started with the transistor. This is the symbol for a transistor. It has 3 terminals: the base, the collector, and the emitter. There are 2 types of transistors, specifically the bipolar junction transistors, with the NPN and the PNP transistors. In our case, we'll only look at the NPN transistors. That's because those are the ones I have around. If I had the PNP, we'll also go through that perhaps in the future. A transistor is a tiny device with 2 main jobs. One is to work as a switch. It can turn a current on or off. The second is to work as an amplifier to make a small current bigger. We can use a transistor to amplify a small signal into a much larger signal. However, in our case, we'll just focus on the transistor working as a switch. It has 3 parts: the base, which acts as the control. Then there's the collector, which is the part where the current comes in, and the emitter, where the current goes out. Note that we'll be using the conventional flow of current, which flows from the positive to the negative terminal or ground. So how does it work? When you send a small current to the base, it essentially opens the gate or acts the same way as a switch on your wall would. You flip it on and your bulb goes on. Same thing here, but without the moving parts. If no current goes to the base, then the switch is off and no current flows. If current goes to the base, the switch is on and current flows. You can also think of it just like a tap or faucet. The collector is like the source of water or the water pipe where the water is coming in, and the emitter is where the water is coming out or the tap. The base is like the handle that you can turn to either make water come out or close it. And in very much the same way, if you turn the tap slightly, only little water comes out. If you turn the tap fully open, then more water comes out. And it's the same thing here. If a small current is passed to the base, then some current flows, but the more current that flows into the base, the more current will flow from the collector to the emitter. And that's how a transistor works, just like a switch. Now that we know that, we can try to combine some of these transistors in ways to create these logic gates. I have made 3 of them: the AND, the OR, and the inverter. And let's go through each one of them and see how they look like on a breadboard. And this is the schematic, sort of rough schematic that I've come up with for the inverter. We have the LED, which is the one that looks like a triangle with some arrows coming out from it as the output. The LED will light when there's current flowing through it, and it will stay off if there's no current. I've connected the transistor to the same power supply as the LED. Then I've put a switch at the base of the transistor so that we can turn it on or off. The zigzag looking component is a resistor. Then we have our 5 volts, which would be the positive terminal in a battery, sort of. Then there's the ground, which is like the negative terminal. Remember, for the inverter, when the input is 0, the output is 1. When the input is 1, the output is 0. In our case, 0 will be represented by the LED being off, and 1 will be represented by the LED being on. So for this one, let's go through some finer details of how it works. When we turn the power on without connecting the switch, then the LED lights up because our input is 0. When the switch is open, our input is 0. So the LED is on because the transistor is off. So the current will flow through the LED. And this works just as we saw in the inverter. When the input is 0, the output is 1. When we close the switch, the transistor is on and it allows current to flow from the collector through the emitter to ground. The reason the LED goes off is because the transistor offers a lower path of resistance for the current. So instead of going through the LED, the current goes through the transistor to ground. In this way, when the switch is closed, our input is 1 because the transistor is now on, and the output is 0 because we see the LED goes off. This is a simplified explanation of how it works. For the others, we might not go into details of how to construct them, but we'll see how they look like on a breadboard. Here I have constructed the circuit we saw in the diagram on a breadboard. I have used an old phone charger as the power supply. It provides 5 volts at a maximum current of 500 milliamps. The green LED is to show me whether there's power. The blue LED I'm using to show the input. When the blue LED is on, then the input is 1. When the blue LED is off, then the input is 0. The red LED represents the output. When the red LED is on, then the output is 1. When the red LED is off, then the output is 0. And the button I'm using as the switch. And when I press the button, then the input is 1 and the output is 0. When I let go of the button, the input is 0 and the output is 1. And thus, we have successfully made an inverter using transistors. To be more specific, I used the 2N2222 NPN transistor. And I'm using 1 kilo ohm resistors here, the AND gate. And this diagram shows the symbol for the AND gate and the rough schematic for how you can make an AND gate from transistors. And we can see that both A and B have to be on for current to flow from VCC or the 5 volts to ground through the LED. I've just replaced the switches with A and B, which will be our inputs. Remember, in an AND gate, both A and B have to be on for the output to be 1. Otherwise, if only A or if only B is 1, then the output will be 0. And if both A and B are 0, the output will remain 0. I have also wired up this schematic on the breadboard, same power supply, but now I have 2 buttons to represent A and B. And note that when I click one of them, the LED remains off. Sometimes the LED lights slightly, but that's because of the value of resistors I'm using. Otherwise, it remains off. It only goes on when I press both buttons together. In this way, we have made an AND gate on a breadboard using transistors. I'm using the same transistors I used for the inverter. The OR gate. The OR gate's output is 1 when either of its inputs is 1. Or when both of them are 1, the output will still be 1. And this is the symbol for the OR gate and a rough schematic of making it using transistors. When either A or B is on, then current will flow from the 5 volts to ground through the LED. I've also wired this up. Let's see how it looks like. Same power supply, and I've connected 2 blue LEDs to the buttons to show the inputs. When I press either of the buttons, the output, which is the red LED, goes on. Hence, we have made an OR gate when either of the LED is on, or when our input is 1, for either of them, the output is 1. Also, when I press both of them, the output is still 1. Now that we have seen how to make the logic gates using transistors on a breadboard, the next step of our journey is integrated circuits. Many electronics contain dozens, if not hundreds, of transistors, let alone the billions inside a CPU. And as you have seen, it took a lot of space just to make some simple logic gates. You can imagine what would happen if you were to make an entire system using this method. Unfortunately, we don't have to. We can use integrated circuits. An integrated circuit is a tiny chip made of silicon that contains a collection of electronic components such as transistors, resistors, capacitors, and diodes, all packed together. And this is very useful. For example, we'll see some integrated circuits that contain many of these logic gates together, which will make our work so much easier. For example, here is the SN74LS08N. 74LS08 is a quad 2-input AND gate. What this means is that it contains 4 AND gates inside. And we can see that the part number is written on top of the chip. If we were to take a look inside this integrated circuit, this is what we'd see. We'd see 4 AND gates arranged in this order. And such diagrams are known as pinouts. And we can see that each pin or sort of legs on the chip have a number, and each pin has a specific function. Some are inputs, some are outputs, and some are for power. There are many types of integrated circuits out there, each containing very different components and many different specialized functions. For example, we could have some integrated circuits for memory, some integrated circuits for OR gates, NOR gates, NAND gates, and so on. We'll see some more in coming examples. Now, these integrated circuits are usually categorized into logic families depending on the components that are used to make them. For example, in the case of logic families, or these integrated circuits that contain logic gates, there's the bipolar logic families, the CMOS logic families, and the BiCMOS. Now, we won't look into that, but this usually just determine the speed, the delay, and other things like the amount of power required to run them, and so on. In our case, we'll just be using the parts that we have, regardless of the logic family. If you had a chip like the LS08 that we just saw, we can go to the manufacturer's website and get more information about it. For example, the LS08, the 74LS08 is made by Texas Instruments. And when you go to their website, we can see information about it, including the part number, the different form factors, and we can even get the pinout and more information about the chip, including how it works and even the internal schematics of the chip. This may not be necessary for all of them, but it's good to know in case you find yourself with any of these chips and you want to know how they work or what is inside them. We can always go to the manufacturer's website and get more information. These are some integrated circuits I had bought online. Specifically, these are the 74LS08, which are the quad AND gate. So this IC contains 4 AND gates inside. I'll use them to create an AND gate instead of using the transistors as we had done earlier. I can wire them according to the pinout we had seen earlier. I've connected them on a breadboard and I used the pinout to decide which gate to use. I've used only one of the gates, and you can see that it lights only when I press both of the buttons. So it works. And this chip contains 3 other AND gates we can use. And we'll see more of this in upcoming videos, the way we can also combine other integrated circuits together to create one full logic expression. We've come to the end of the video, and let's look at what we've covered so far. We've looked at what logic gates are and the different types, like the AND or inverter, NOR, NAND, XOR, and XNOR. We've also looked at how the logic gates are made using transistors, and we've been able to do some experiments and see whether they work. We've also looked at integrated circuits, and we've also seen some examples. This will form a good basis of understanding for the rest of the topics that we are to cover, like Boolean algebra. There's so much more to cover on digital electronics, but I hope this video helped you understand a thing or two. If there's anything that I missed or you wish I would have covered in this, please let me know. Thank you for taking your time to watch this video. I hope to see you in the next one.